Good morning. This is Group 18 presenting reinforced credit card fraud detection using quantum machine learning. For our background and introduction, traditional fraud detection systems faced a number of challenges, with the major one being high false positives and limited scalability, whereby a system is unable to process vast amounts of data at a certain time. And our proposed solution to these problems was building a hybrid quantum classical framework that utilizes classical algorithms as well as quantum computing algorithms to be able to detect fraud in credit card transactions. Specifically, we integrated extreme gradient boosting with quantum neural networks for improved accuracy, faster processing, and lowering the rate of false positives. We had metrics that we evaluated this framework with metrics such as F1 score to validate the model's effectiveness. In the work done currently in the field, recent advances in machine learning have demonstrated significant improvements in fraud detection when quantum algorithms are implemented. But we have a gap in that whereby there is limited hardware, such as quantum processors. And also in the recent literature, hybrid quantum classical approaches have emerged as promising solutions where quantum processors handle complex feature instructions while classical systems perform optimization tasks, and therefore achieving superior computational efficiency compared to the traditional method. And of course, here significant technical hurdles remain in achieving seamless integration between quantum and classical computing systems, particularly in data transfer and processing architectures. Our domain application problem revolves mainly around improving accuracy and efficiency of credit card fraud detection systems, while our computational problem is centered solely on overcoming the limitations of credit card fraud detection systems, especially in handling large-scale data and high-dimensional data, as well as noisy transactional data. Thank you.
Through the research objectives and the data collection, which is pre-processing credit card transactions with model building. Then there is performance testing that includes measuring accuracy and recall. Then we also have a challenge that we had to study, which were quantum noise, overfitting, and so many others. Then the research questions were, can quantum models improve fraud detection? The best hybrid architecture to use for the model development, and how much speed with quantum parallelism. Then the model architecture, this is our model architecture, it looks like the steps that we followed to implement the training of that data set. Then this also had an EDA, and this is what we got. We had scatter plots, we had histogram bins, we had box plots, as well as so many others. Then these were our results that we got from our different models that we trained. For example, as you can see, we have about 6 models, and accuracy, physical and recall were also put in the table. Then we also used AI to test our model, whereby we also got visualizations, use feature import tests using random forest, use Sharp, as well as line implementation to actually get the study and the distribution of the model. Up to my next presenter.
Thank you. I'm Emerson Mutakanda, and like start from where my colleagues have talked. Like the model selection, then deployment, like we chose the XGBoost neural network or like quantum neural network because we are for it for deployment. So like had the precision, then the forward like had the highest percentages. Then why like the reason why we chose this type, the strong learning capability, like as demonstrated the deep learning of crowd patterns by depending both robust task rather boosting. Then also balance accuracy, as like what you the highest accuracy of 89.98, negating expected generation like without overfitting one and C transactions. Then the efficient feature selection, like using sharp, as my colleague has explained. Then also quantum advantage, like the quantum neural networks, like contribute to fast and then data processing, which minimize the error. And also we had the effortless like cloud deployments, which have like the model into a simulable web app for the user-friendly access, like deploy the scalable backend with fast API then they like integrate into like a real financial system, containerized it like the model using the doc and then deploy it on the cloud. This is our model selection and then like the deployment whereby we first selected the data, then like the data set, then we got the model and we trained it. Then after training it, we save that model, then you uploaded that on the that storage model. Then from there will be the distributed application, whereby I had a deployment on me, the cloud. And then from there, like go to the public API, like API URL generated, whereby as you come here, this is the like the end user, whereby he can use that public URL, like interact with the system, whereby he can put the data, then fire that interface, and then you get predictions. Then the demonstration like of the product, of the IP assets, and then others as my colleagues has explained. This is the expressions for the demo, like this. Then I will come back and then we show like how it works. Let me welcome my colleague.
Was afraid. That is how the conclusion whereby we developed a model which improves critical fault detection by combining the strength of classical XGB boost and the quantum neural networks. Then it enhances fault detection rates by balancing the accuracy and computation. Then we have the model that shows strong potential for real-world application by leveraging quantum enhancements alongside classical machine learning. Under the limitations, we have the computational overheads, whereby the quantum models are resource intensive, whereby they require large CPUs and have the scalability issues, limited qubits, which restrict handling large data sets. Then you have data pre-processing complex and quantum noise. These models are highly affected by noise. Then you have optimizing quantum search and use of hybrid quantum classical techniques to reduce overhead, which can be used as well. Under the next steps that we need to improve the XGB quantum networks, improving the architectures which can reduce their computation cost. Then you have the testing model on real quantum hardware instead of simulators will provide much insights onto the real-world performance. Then you have other work which can improve model interpretability and developing explainable quantum algorithms. Then integrating additional quantum machine learning techniques. And a good example we have is variation quantum classifier and quantum support vector machines, which can enhance fraud detections. Then expanding the data sets with real-time transactions from the banks, which can make the system more dynamic and reliable. Then we were finally building a continuous learning system that adapts to evolving fraud patterns. Under the acknowledgements, we have Mr. Gary Wango Marvin, who has done as well in their contribution, thus understanding how the course moves. Then our sincere gratitude goes to the Unipod and the Intellectual Property Office at Makerere University. Yeah, then we appreciate the valuable insights about ChatGPT plus the black box, which will provide a lot of the help. Thank you.
Let's go to the system demo. Okay, thank you. Like this. like this is our interface whereby like you can enter your transaction details, and as you can see that the transaction amount, then you can see receivers previous balance, that's the old balance, then senders previous balance, and then from there you can select, like there's a button here, addition transaction feature, can select step time or taken as one, then you can select city, transfer, cash out, pay network. So now let me take the asset transfer. When you try to analyze, you can see that fraud has been detected, so it blocks the transaction, then flag the account. As you can see that the model confidence that there is fraud, this is like 56. And then here can like see the transaction summary, which is here, like the time, then the details, step one, like the amount or the balance, and then the prediction finally. Then let us analyze another thing, like if it is not, if it is none, then we try to put here something like this. Then let it be like step, let me put like 5. And then let it be like a cash out. Then when you try to analyze, it's also still fraud. That's all from group 18. Thank you.